Okay, I'm good. So let's begin our presentation.
Okay, so hi everyone. I will start by discussing what we did to improve the performance of our regressor. So our main objective was to minimize MIC on the cargo leaderboard, but we also wanted the model to be stable and interpretable. The first major improvement we made was applying a log transformation to the target variable. The insurance charges are high right as good, especially due to smokers who have extremely high costs. Without transformation, the model tends to over-focus on those extreme values by using log transformations through a transformed target regressor. So we reduced variance instability and improved our overall prediction accuracy. And second, we focused heavily on feature engineering. We introduced nonlinear features such as age squared and BMI squared to capturing the data. We also added interaction term like age multiplied by BMI and a smoker multiplied by BMI. These interactions are important because the impact of BMI on medical costs is much stronger for smokers than non-smokers. By including interaction features, we allow the model to better represent real-world relationships. And what's more, we implemented structured segmentation. Instead of feeding a single model to the entire dataset, we tried separate models for smokers and non-smokers. The cost structure between those two groups is fundamentally different. By splitting the dataset, each model learned more specific patterns, which reduced errors significantly. Finally, we use XGBoost as our base regressor. XGBoost is well suited for tablet data and handles nonlinear relationships effectively. We tuned hyperparameters using cross-validation to ensure improvements were consistent. Overall, our performance gains came from transformation, the target, engineering nonlinear features, segmenting structural differences, and using a powerful tree-based model.
Okay, for the next part, I will explain how we assess and improve the fit of this regressor. Improving leaderboard performance alone is not enough. We need to verify that our model generalizes well and is not overfitting. First, we use K4 crossing validation. Instead of relying on a single train test split, we arrange MSE across multiple folders. We compare training MSE and cross-validation MSE to detect a potential overfitting. The gap between them was relatively small, suggesting the model generalizes well. Second, we dropped the learning curve. This was especially important for diagnosing bias variance trade-off. The learning curve plots training and validation error as training sample size increases. In our case, the curves gradually converged and the validation error decreased as the data increased. This suggests that the model has balanced bias and variance, and additional data will provide only marginal improvements. Third, we conducted residual analysis. We plotted predictive values against residuals to check for systematic patterns. The residuals appear randomly distributed around zero, which indicates that the model captures a nonlinear structure responsibly well. Through these tools, cross-validation, learning curves, and residuals plots, we ensured that improvements in performance were supported by diagnostics evidence and not just later broad results. So my teammate Louis will tell the rest of the presentation.
In my part, I will briefly add a reflection. One key insight from this project is that performance improvement and model fit evaluation must go together. Increasing model complexity reduces bias, but it can also increase variance. Our feature engineering and segmentation reduces bias, while cross-validation and learning curve diagnostics helped us control variance. We also learned that a lower MIC on cargo does not automatically mean a better model. Diagnostics tools are necessary to confirm generalization. Overall, our final model represents a balanced bias variance trade-off, supported by both performance improvement and structured fit evaluation. Thank you.